So as we mentioned together, okay, of course, the resistance will be higher. So you have the resistance in if you go to your appendix, the resistance value, okay, is given for the whole spherical area. And since you are not able to propagate your heat from this whole area, you are limited only by 1/3 of the area. Okay, then since the area is divided by 3, and we know that the resistance and area are inversely proportional, so you will take the formula of R, but you will multiply it by 3. Okay, so this is the only trick here. The remaining part is easy. So what do we have here? You have first, you know that from the internal side, the temperature of the eye is larger than from the outer side. So heat will be dissipated from inner side to the outer side. Okay, and it will, of course, we have several resistances that will indicate what is the heat rate of dissipation. So first, that's why this will explain for you, and this problem will explain for you why when we put contact lens, we feel hotter sensation for the eye. Because what will happen when we put the lens? When we put the lens, we have higher resistance to heat transfer. Exactly. So whenever you have a higher resistance to heat dissipation, this will lead to a higher warm sensation for your eye. Okay, and we can calculate this here. In this problem, we can calculate the variation in temperature if we have contact lens or if we don't have them. Okay, so if we don't have contact lens, what will happen is the following. You have first convection from the inner side. You have conduction in the cornea of the eye. Okay, and then convection to the outer side. While when you put your lens, you have an additional layer that will do additional resistance of conduction, okay, which will reduce the dissipation of heat to the outer side, and this will lead to hotter sensation for your eye, okay, and we can see this in values. So we will compare the case of with and without lens. So first, as we said, if we don't without the lens, okay, we have first the resistance to convection. Look, you know that the formula of resistance to convection is 1/h times A, okay? And here, as we said, the area is the total area of the sphere over 3. So this area will be A lateral of sphere over 3. That's why we can take 3 to the upper side. So it's 3 over H inner times lateral area of a sphere. And the formula for the lateral area of the sphere is 4 pi r square. So from the inner side, okay, you have to consider r inner, which is here r1, okay? So it's 4 pi r inner square. So the total resistance to convection from the inner side is 3 over H inner times 4 pi r inner square. Okay. Now, when you consider the case without lens, you have just one resistance to conduction. And please pay attention. In case of a sphere, in the electrical circuit, you cannot put Q prime, you cannot put Q second rung. Okay. Because here only the rate is constant in steady state conditions. Here you don't have per unit length because in the cylinder, okay, we have propagation with radial direction and the length is constant everywhere. But here for the sphere, you don't have this. It's you have a spherical shape, okay? So or you will talk about heat rate or you will talk about heat flux Q second. And of course, Q second is not constant. Why? Who can tell me why Q second is not constant?
Because of the change of area.
Very good, because of the change of area. So Q is constant, the rate, but the rate is equal to Q second here times a lateral area at each radius over, for the sphere, okay, over 3, because we just have 1/3 of the area. So as the radial, the radial coordinate will increase, AR will increase, and Q second will decrease because of steady state conduction. Okay, so Q second will decrease as we go from the inner to the outer side. Okay, now if you go to your table or appendix, they give you the expression of the resistance to conduction in a sphere. This resistance is of the following form: 1 over 4 pi k, and you can prove this formula as we did for the cylinder in class. Okay, so 1 over 4 pi k times 1 over Rn minus 1 over R out. So this is the formula for the resistance developed in case of spherical coordinates. And since you don't have the total area of the sphere, you just have dissipation through 1/3 of this area, should multiply here by 3. Okay, and R inner is R1 for this layer, and R outer is R2. While now, if you want to consider after the case of putting lens, you need to add another resistance to conduction, and then you will do R inner will be R2 and R outer will be R3. Okay, now for the first case, we don't have this. We just have dissipation to the outer side by convection, and the resistance to convection is similar to the form of resistance to the inner side. Just what will change is instead of Hn, you put H out, and instead of R1, you put R2, because at the outer side, you have R2. So this is your circuit without lens. Now with lens, as we said, we have to add a resistance to conduction because of the lens layer. Okay, so as we mentioned, for the lens, the inner radius is R2, and here we put 1 over R2, while the outer radius is R3. So we'll add this resistance to the circuit, plus, and of course, we use K of lens. And finally, you have from the outer side also the area changed because you have increased thickness. So now instead of 3 over H0 4 pi R2 square, you will use 3 over H0 times 4 pi R3 square. Okay, so this will give you the resistance to convection. So now, of course, the resistance to convection was reduced because the increase in area. We know that the area is inversely proportional. It's true that this term is smaller than this one, but you added a conduction term. So, and the conduction term addition will be dominant. This will explain, if you want, the variation in dissipation rate. Okay, so if we compare the two values, okay, without lens, we have a rate of 451.1 Kelvin per watt. Okay, which is this is the value of the total resistance, and this is the value of total resistance with lens. Here, if you want, in case if you want, the thickness of the lens was really small, the reduction of convection will be dominant. Okay, so that's why it's important to work on the property of lens. When you have good properties, you might have, when putting lens, lower resistance, which will explain, if you want, then the value of loss rate from your the increase of value of loss rate in case you have you are putting your lens. Okay, so depending on the conduction resistance compared to, so as we said, we have increase in conduction resistance and reduction in convective resistance. This will affect then the variation of the total rate dissipated from the eye. Okay, so this is why you have, in some cases, you put lens, you say it's very comfortable. I don't have warmer sensation. While in other cases, they can harm your eye. Okay, so you need, this is why they optimize, if you want, the thickness and conductivity of the lens anyway to have better conditions. Okay. Question on this? Okay. Another problem. Do you hear me again? Dear students, can you hear me now?
Yes.
Dear students, do you hear me?
Yes, doctor.
Yes, doctor.
I just had a small connection issue. Do you hear me now?
Yes.
Okay.
Yes, doctor.
So, in this case, in this problem, we consider one-dimensional conduction in a plain composite wall. The outer surfaces are exposed to a fluid at 25 degrees and a convective heat transfer coefficient of 1000 watt per meter square Kelvin. The middle wall experiences uniform heat generation, Q dot B, while there is no generation in walls A and C. This is a very important problem. The temperatures at the interfaces are T1 equals to 261 degrees and T2 equals to 211 degrees. In this problem, it's we should pay attention that we have generation not in a thin layer, in a layer with a certain thickness. And therefore, we should take care to not include this in the thermal circuit, okay? And we'll have two different points. We have the generated heat here will be dissipated from two sides. One will be dissipated through material A and then convected out. And another part will be dissipated through material C and will be convected out. But since it's not a very thin layer, we have two separate points. And if you want to deal with a thermal circuit, we can draw two circuits, one from T1. And what is good here is that they gave us T1. Okay, so we know the value of T1. We can draw an electrical circuit from T1 to T infinity. So we have to include the resistance to conduction in A, then the resistance to convection with this side, okay? So this is resistance to convection from this side until reaching T infinity. While so this is a separate circuit. We need to draw another circuit for the other side. But between T1 and T2, we cannot put anything here, okay? So because here we have generation, so we need to deal with it using differential equation and integration to find the variation of temperature here. We cannot consider it within the thermal circuit, okay? Now from the other side, we have T2, we have resistance to conduction in material B, and we have finally since we have in material C, and we have finally the resistance to convection. Okay. And here, since we have same properties, T infinity and H, so the convection resistance from this side will be equal to the convective resistance from the other side. Now, they want us first, assuming negligible contact resistance at the interface, to determine the volumetric heat generation Q dot B and the thermal conductivity KB. We have two unknowns in this problem, Q dot B and KB, okay? Let us think first about Q dot B. In order to find the value of Q dot B, we need to do a small analysis about how the rate will be divided in the system. So as we said, we have dissipation from two sides. So what is generated in material B will be divided into a Q, we can call this, if you want, a Q1, and this is Q2, okay? So the heat rate, the total heat rate generated in B will be divided into Q1 and Q2. And how we calculate the total heat generated in B? We know that Q dot is in watt per meter cube. It's a volumetric generation, watt per meter cube. So to get the rate, the total rate in watt, okay, of generation, it's equal to Q dot B times the volume. So it's Q dot B times the volume of generation. And the volume of generation is the volume of this part of material B. The volume of material B is the thickness of this material times the area of the wall. So we can replace QB by Q dot B times 2LB times the area, okay? So this is how we calculate, this is the expression of QB function of Q dot B. And this generated rate is divided into Q1 plus Q2. So to be able to calculate Q dot B, which is one of our unknown, the first step is to find the Q1 and the Q2. And as we said, to calculate Q1 and Q2, we can do it from the thermal circuits, because what is propagating in this side is Q1, and what is propagating in the other side is Q2, okay? And since they gave me T1, T2, and we have T infinity, I can calculate Q1 as T1 minus T infinity over summation of these two resistances. And Q2 is T2 minus T infinity over summation of the two other resistances. And in this way, I can solve for my first unknown, which is Q dot B, okay? Now to get the conduction of material B, then I cannot use thermal circuits, because as we said, in material B, we have generation. So I need to go back to my differential equation. If you remember, in B, we have the case of steady state conduction with generation, okay? So if we use the integration method as we developed in the course material, we can write T of X as minus Q dot over 2K X square plus C1X plus C2. And we know that to get the boundary conditions C1 and C2, all we have to do is to apply the conditions. Here in this problem, this is our material B, okay? If we take the axis at the middle, so let's say this is y-axis, and this is x-axis, we have the thickness is 2LB, okay? So we have at this level x equal plus LB, And at the other side, and we have the temperature here. At x equal plus LB, they provided us with T2. And at x equal minus LB, the temperature is given to be T1. So first I can apply these two conditions, okay? But of course I have to add in an equation. Why? Because what are the unknowns in this equation, T function of x? I need C1, I need C2, but also I have KB, which is the conductivity, okay? So, but I already determined, if you want, I already determined what is heat rates that will dissipate from the side. So I know what is a Q conduction. Q conduction at x equal minus LB is equal to Q1 that I already calculated, okay? And the Q conduction from this side is equal to Q2. So you can see in this problem, they gave me extra information. No need to give both T1 and T2. They can just give one temperature and the other can remain unknown because I can write 4 equations. And here they helped me in the calculation. So the first equation will be just a verification. I can say that Q2 is equal to Q conduction at x equal plus LB, okay? And while Q1 is Q conduction at x equal minus LB. So I have the possibility here to write 4 equations. The first one is T at minus LB is T1. The second equation is T at plus LB is T2. So I have 2 equations. And since I can add 2 other equations, which is that the conduction flux, if I want to Q second at minus LB, I just have to apply the formula. What is Q second at minus LB? It's minus KB times dt by dx at minus LB, okay? At minus LB. So I can write, this is my equation. I can derive it with respect to x. So I get that dt by dx is equal to minus Q dot times x over k plus C1 okay? So now I can apply this equation at minus LB and at plus LB. So I can write that Q second at minus LB is minus KB times the derivative of T with respect to X, and I replace now X by minus LB as I did here, okay? Here, it's enough to write 1 equation because I only have 3 unknowns. But in case they didn't provide you with both T1, T2, they gave you just 1, you will have 4 unknowns. So the first equation that will close your system will be the following. You will have Q second X at plus LB equals to Q second 2. And please pay attention for what they did here. They considered Q second at minus LB to be minus Q second 1. You know why? Because Q second 1 is in the negative direction. Now we got the absolute value of Q second 1. So we did Q second 1, Q second 2, summation of them equal to the generation term, okay? Because we have And we considered here absolute values. We expressed this as a positive quantity going from T1 to T infinity, and Q2 as positive quantity flowing from T2 to T infinity. But here, when you want to express in one coordinate system, and when you want to take material B, you have only one positive direction. We'll take this is the direction that is positive. So when you compute the Q second at minus LB in your equation, you will get a negative result because the rate is flowing backward. That's why pay attention here to put, when you put Q second minus LB, you put minus Q second 1. Okay, while when you put Q second at plus LB, it's in the positive direction, you put plus Q second 2. So you should pay attention for this. Okay, so the first equation can be Q second at plus LB is equal to plus Q second 2, because Q second 2 is already in positive direction, equal to minus KB dt by dx at plus LB. So here, instead of minus, you will put a plus, and then you will get your force equation. So here, if you want to simplify calculations, they gave us extra information. And you can use the force equation just for verification. While if they want to make it more complex, they can give you just T1 or just T2, and then you will have a system of equations to solve. Okay. Any question on this? Okay. So here, now you will see that ideas are very similar. Okay. So just we have always to determine what type of coordinates to use and how to draw our circuit. So in a nuclear reactor, fuel elements consist of a solid cylindrical pin of radius R1 and thermal conductivity Kf. The fuel pin is in good contact with a cladding material of outer radius R2 and thermal conductivity Kc. Consider steady state conditions for which uniform heat generation occurs within the fuel at a volumetric rate Q dot, and the outer surface of the cladding is exposed to a coolant that is characterized by a temperature T infinity and a convective coefficient H. We want to obtain equations for the temperature distribution within the two material, within fuel and cladding respectively. And then we want to express the results exclusively in terms of the given variables. So here, just we need to know that whenever we have two materials, and you have two materials in contact, you have first the fuel element, and in the fuel element you have generation, okay? While in the outer annulus, you have the annulus that is covering the fuel element, you have pure conduction, okay? And you want to solve, you want to just write the equations and put how to solve for your unknowns. What is very important here is to know that always in steady state condition, at interface, okay, we have the same temperature and we have the same heat flux. So here you can say that at R1, I have continuity in temperature and continuity in heat rate. So I can write that the temperature of fuel element at R1 is equal to Tc at R1 and also the rate of conduction in material F. So Q second, of course, Q second in fuel element is not constant because of generation. That's why I need to determine QF at R1, which is calculated by minus K F times dt dTf by dt, by dx, sorry, by dr, dTf by dr at R1 okay is equal to q second c in the annulus, and in the annulus material we have constant conduction rate because conduction flux. The conduction flux is not constant, the conduction rate is constant. Okay, so it's equal within the material, we are saying. But if we take the interface, at the interface layer, it's one radius. So you have same q second in fuel and q second in the annulus. Okay, while at this level, while whenever you propagate in the annulus, of course, the rate will remain constant because here no generation, but the flux will be reduced because of the increase in area. And we can just write the condition at the interface that q second fuel element equal q second annulus at R1. So equal to q second C at R1 equals to minus Kc so equal to minus Kc times dt by dr at R1. Okay, so these are the continuity equations. Now we have to write other equations because we have several unknowns. How many unknowns we have here? We have two materials. You need to write the equation in material 1. So in the fuel element, you have already C1 and C2. And also in the annulus material, you have two other constants unknown, C3 and C4. So in total, you have to solve for 4 unknowns. Because you have 4 unknowns, you need to write 4 equations. We have already considered the 2 continuity equations. We still need to consider in each material what can we use. Okay, so you have first that within the fuel element you have symmetry. That's why the temperature gradient at the center, okay, will be 0. So you will have maximum temperature at the centers and will have dissipation in all directions. So we can say that because of symmetry in the fuel element, we can write that the maximum temperature is occurring at the center. So dt by dr for the fuel element at the center is equal to 0. We already have written the 2 continuity equations for temperature and rates at the interface. And finally, we have the outer condition. We have convection at the outer side of the annulus. So we can say that Q conduction at R out equal Q convection. So these are the 4 equations that will allow us to solve for our system. Let us go again over these equations. So first you say, since you have generation within the fuel element, the equation is 1 over R d by dr. df by dr is minus Q dot over K. And then you integrate it twice to get the expression of the TF within R, okay? And you have 2 unknowns to determine, C1 and C2, while in the annulus, you don't have generation, okay? So whenever you integrate, you don't get this term of generation. You just get C3 over Kc ln R plus C4. And your 4 unknowns are C1, C2, C3, C4. This is to solve this system, you need 4 equations. So as we mentioned, we have 2 continuity equation at the interface, and we have for the fuel element due to symmetry 0 gradient at R equals 0, while for the annulus we have the outer condition of convection. So these are the 4 equations. The first one, as we mentioned, is due to symmetry in the fuel element. Maximum temperature will take place at the center. So dt by dr at r equals 0 equals 0. This will give you equation number 1. Then you use continuity equation between the fuel element and the annulus. You have continuity of temperature. So at the interface, same temperature at R1 and same heat flux. Okay. So these are equations 2 and 3. And finally, as we said, the first equation is obtained because of the convective condition from the outer side. So minus K in the annulus times dt by dr in the annulus at R equal R2 is equal to the convective flux, which is H times Tc at R2 minus T infinity. So you have just a system of 4 equations, 4 unknowns. You just have to replace your variables. You have everything except C1, C2, C3, C4. So once you solve for this complex system of 4 equations for unknowns, you can determine the temperature profile in your fuel element and the temperature profile in your annulus. And then once you get your equations, you can evaluate any temperature that you want. For example, here they are asking to evaluate the maximum fuel temperature. So as we mentioned, the maximum fuel element temperature will occur at the center line. So if you replace R by 0 in this equation, you will get what is the temperature at the center line, which is the maximum temperature in your fuel element. Okay. Any question on this?
No, doctor.
Okay, thank you for your time. Bye-bye.
دكتور الريكوردينج بس وين بينزل؟